Today I'm going to cover 7.1, approximating integrals. I'm going to start right off with an example. Let I be the integral from 0 to 1 of sine of x squared dx. I'd like to calculate a left and right Riemann sum approximations using 100 subintervals. As discussed previously, we can write these with sigma notation, and we're going to simply multiply the height of each rectangle times the width of each rectangle. The width being 1 over 100, and for the left approximating sum, we'll start at f of 0, and we'll end at f of 0.99. For the right approximations, we're going to start with f of 0.01 and end at f of 1. Using a calculator, we get the left approximation to be 0.30607, and the right to be 0.31449. The difference between these two estimates is very small, 0.00842. Let's take a look at the graph for a second. If I graph y equals sine of x squared between 0 and 1, I notice that this function is increasing entirely over the interval. We call that a monotone function over that interval, meaning it is strictly increasing. Now let's go back to the estimates. Since I know that because my function is increasing, the left approximating sum is going to be less than the actual answer, and the right approximating sum is going to be more than the actual answer. Therefore, my answer is going to be somewhere in between those two values, the actual integral value. If I average my left and my right approximations, I get 0.31028. Now, if I use that as my estimate for the integral, then that tells me that the actual integral has to be within half of 0.00842. Because from the midpoint, I'm 0.00421 away from the left approximation, and also 0.00421 away from the right approximation. So I know that my error bound is going to be less than or equal to 0.00421. Let's look at a generic example for a minute. Let's say we have a function f that is strictly increasing, or it could also be strictly decreasing, but let's just say that it's monotone over the interval from a to b. As you can see, the red rectangles represent the left approximating sum, and if I go up to the top with the blue for the rectangles, that would be the right approximating sum. So the worst case error is going to be the area of each of those boxes added together. We know that the error is actually going to be at least a little bit less than the total area of these boxes. Now, to put this in perspective, I could actually take, since each of these boxes have the same width, I can slide them all over and stack them up. And if I stack them up, I get that rectangular area, which represents my worst case scenario for the error of my approximating sums using either the left or the right. And I know my function is going to have a value somewhere in between those two approximations. So what's the area of this purple rectangle? Well, it's f of b minus f of a, that's the height, times my delta x being the width of each subinterval. So that leads us to a theorem. Suppose that a function f is monotone on a closed interval ab, and let I be the integral from a to b of f of x dx. then the absolute value of the difference between the actual value of the integral and a right approximating sum using n subintervals will be less than or equal to the area of that purple rectangle, which will be f of b minus f of a times delta x. And delta x is calculated by taking the length of the interval and dividing by how many subintervals we have. The absolute values around the f of b minus f of a are important because in my picture, I had the function increasing, but it could just as well be decreasing, as long as it is monotone, which means increasing or decreasing. Likewise, the error bound for the left approximating sum will be exactly the same. Worst case scenario, it's that purple rectangle, the area of that, which is f of b minus f of a times delta x, which is b minus a over n. And if I use a trapezoidal approximation, which is the average of the left and the right, then my error will be half as much. So it's the same error bound as the left and the right divided by 2. So now we have 3 error bound formulas for left, right, and trapezoidal approximations, as long as our function is strictly increasing or strictly decreasing. So let's try this example. How large must n be to ensure that a left approximating sum with n subintervals estimates the integral from 0 to 1 of sine of x dx with an error less than 0.01? Well, let's use our error bound formula. Since we know the sine graph is strictly increasing between 0 and 1, here's our sine graph. So the theorem does apply, so I can use the error bound formula. I want that to be less than 0.01. So f of b minus f of a, well, that's simply the sine of 1 minus the sine of 0 times b minus a, 1 minus 0, over n. And I don't know what n is. I'm trying to figure out how many subintervals I need to have an error less than 0.01. And since we're going to have some fractions, let's go ahead and write that as 1 over 100. Now, if I do sine of 1 minus sine of 0, I'm going to get 0.8415 times 1 divided by n, less than 1 over 100. So if I multiply both sides by 100, I get 84.15, and multiply both sides by n. That will not change the inequality because I know n is a positive number. I get n has to be greater than 84.15. Now, since n represents subintervals for a Riemann approximation, I know they have to take on integer values. So that tells me that 84 would be too few, and I would get an error that's more than 0.01. But as long as I set n equal to 85 or more, then my error is going to definitely be less than 0.01, or 1 over 100, based on my error bound formula from the theorem.